Okay, welcome my friends to the Physics Fundas. I'm going to start the new series today. It's ray optics, and I'm really excited. And this is going to be a multi-part series. Today, I'm going to give you an introduction about what is ray optics. I'm also going to tell you about how the rays behave when they strike a surface, like curved surfaces or plane surfaces. In the upcoming videos, we are going to talk more about how the images are formed, how the microscopes and telescopes work, and total internal reflection and those things. So this one is an introduction. Next week video is going to talk more about it. So in a nutshell, what is ray optics? So ray optics is basically the study of light using rays of light. So this is something that you already studied in your junior grades. When you studied the light, you visualize the light as rays of light. Now, there's another branch of physics that deals with the wave nature of light. So, you are going to study the light itself is really mysterious. It's not mysterious as such, but it has a dual nature. You can visualize the light as being waves, or you can also visualize it as packets of energy called photons. And in upcoming study of the physics videos, you're going to also see how everything is actually dual nature. So, me sitting here right on this chair, I am a particle and I am also a wave. So in short, everything is a wave and a particle. Now the light behaves as waves and particles, but we can just abstract that thing and say it may be either of them, but where is it traveling? So the direction of travel of light is denoted by the ray. So we are going to deal with wave optics in a month from now, but let's get started with the ray optics. So the scope of our study when we deal with ray optics is going to be limited to a reflection of light, a refraction of light, prisms, microscopes, telescopes, human eyes. But when we go to the wave nature of light, we can study more things like interference, diffraction, polarization, scattering. Those are the things that you can understand using the wave nature. So our scope of study for this series of video is limited to these topics over here. So let's again understand what is a ray. So let's say there is a source of light over here. This is a source of light. Now that source of light is emitting the light, but that light travels all over the place in 3 dimensions. So now you can visualize light as being a wave or packets of energy. But look at the direction of travel. Isn't this the direction of travel of light? So that's one ray of light. So what we are saying is, let's say imagine the light. This is a source of light and the waves are produced. Now, as the waves are produced, you can see if I draw a line perpendicular to that, that's going to give me the direction of travel of that wave. So basically, a ray of light is visualized as a line perpendicular to those waves. Or if you can say, no, the light actually is packets of energies called photons. So now the photons are traveling this way. That's all right, but because the ray of light is traveling this way. So when we are studying the geometrical optics, we are not interested in whether it behaves as waves or photons. We are just looking at the path of the light over there. Now, further to that, let's say what happens. Let's say there is a source of light and you can visualize this like this. So let me create a slide here. Let's say there's a source of light, right? So there's a wave that is produced. Now that wave is traveling. Now you can see as you're going farther and farther away, the curvature is reducing, isn't it? The curvature itself is reducing. And as you go far and far away, that curvature reduces so much that that looks like a straight line. It's like, look at the earth standing on the surface of this room. I don't realize that the at the earth itself is a big sphere because look at this. If I'm standing on the earth, this tiny piece, if I look at this tiny piece, to me it's a plane surface. So that's the point. So when the rays of light, let me show you another picture here. So let's say there is a source of light here. Now that curvature that we had, look at when we are far away, that curvature actually disappears. It's more like a flat surface there. And the further you go, the more the curvature looks like a flat thing. Now we're saying the rays of light are perpendicular to the surface. If you go far and far away, look at what happens. The curvature almost disappears, like this room. There is no curvature at all, even though the whole of the earth is curved, but I don't see any curvature. It's almost zero. So now if I'm looking at very far away, this curvature disappears and I look at that wave front, And we'll talk more about wavefront when we speak about the wave nature of light, but that looks like a surface. Now all the lines perpendicular to that surface are going to be parallel to each other. So if this is the surface, I draw lines perpendicular to that, all those lines are parallel to each other. And that is why we say the rays of light coming from far away source are parallel to each other. You have studied that in your junior grades. Light coming from far away is parallel to each other because of this. So that's one thing you got to understand. Now let's move on to reflection. You have already studied this, but let's revise. So what is reflection? There's a ray of light that falls on a surface and it reflects back. Right, kind of like you take a tennis ball and you throw it on this wall, it hits the wall and then it comes back reflected. Even in the case of that ball, if there is no loss of energy and momentum, you will actually see, let me draw what I'm trying to say. So let's say there is a wall here and let's say there is a tennis ball. You throw this tennis ball, assuming no loss in kinetic energy and momentum, you are actually going to see that the angle of incidence is equal to the angle of reflection. Conservation of energy and momentum guarantees that, right? The very same behavior happens here. There's a ray of light that reflects off a surface. The angle of incidence is always going to be angle of reflection. So that is the law of reflection. Now, the second law that you studied was this incident ray, the normal at that point of incidence, normal meaning 90 degrees. So for students who do not remember, so if the light falls here, what you do is you drop a perpendicular as in 90 degrees line to the surface. That's the normal line. Now you measure the angles with that. So this is the angle of incidence with the normal. You don't measure this angle. This angle is not used. So we are basically talking about the angle made with the normal there. Now this is the reflected ray. This reflected ray makes angle R, let's say angle of reflection with the normal. Angle of incidence is equal to angle of reflection, but also the incident ray, the reflected ray, and this normal, they are all in the same plane. Plane as in plane, right? You understand that part, obviously. Now the laws are laws. I mean, so obviously there are laws that are broken in our day-to-day life that police ensures that we do not break. But the laws of nature are the laws of nature. So there is no nothing like breaking those laws at least. So the light can be reflected off a mirror or it can be reflected off a surface like this table. But this table is different because this table has irregularities like this. The mirror can be visualized as a perfect plane there. So are the laws of reflection different? No, they are not different. They are the same. Laws of reflections are the laws of reflection. They will be valid. Plane, smooth surface, a rough surface, plane surface, curved surface, any kind of surface, spherical mirrors, cylindrical mirrors, parabolic mirrors, doesn't matter. The laws of reflection, the two laws are the two laws. Now let's see how that affects the reflection here. So now look at the parallel rays of light reflecting a plane surface as in mirror. So this is mirror, right? And then this is my tabletop, right? I don't have very smooth table. Maybe you have a very smooth table, but even at the microscopic level, that smooth table is not very smooth. It has irregularities. So you can see at both the surfaces, there are parallel rays of light. Now let's try to understand what happens to ray number one here. Ray number one comes in, comes in, comes in. At this point, I'm going to draw perpendicular and I will see the ray number one goes back. Then ray number two strikes here, perpendicular, perpendicular, perpendicular. Now this is not even physics, this is mathematics, right? All these normals will be parallel to each other and that guarantees all these reflected rays go back parallel. So see how beautiful that pattern is. The rays of light coming parallel, they go back parallel. Now look at this rough surface. Things are little different because let's talk about ray number one. Ray number one is incident here. I'm going to draw perpendicular here. But ray number two is incident there. Look at how perpendicular is different. Because see, perpendicular is perpendicular to the surface there. You can see the surface here is this and I'm going to draw this perpendicular. But if you look at, I'll use another color there. So let's say I use this surface, right? This surface has perpendicular there. So you can see all these perpendiculars are not parallel anymore. And then you can clearly see even the laws of reflection are valid. Still, the rays of light that are incident parallel here, they are going all the way. Because see, I'll show that one more time. So this is my surface here. What I'm going to do is I'm going to drop a perpendicular here, a very ugly perpendicular, but that works. And this is angle of incidence equal to the angle of reflection. That law is valid. But then if I look here, the normal itself is this. So this is angle of incidence and this is angle of reflection. So you can see how the parallel rays of light are diffused all over. And that's why it's called the diffuse reflection. Now the specular reflection over a mirror is going to produce images. This produces image, right? You can see your image in a mirror. Now this produces texture. So you can see the texture of the surface, as in surface of this table, or texture of orange or something, texture of this mouse. So all this is possible because of the diffuse reflection. Now let's talk about plane mirror. This is something you've studied in your junior grades. Again, a little revision. This revision is required because many students will get confused when if I directly start over the spherical mirrors, and this is required. This is the backbone of it. So let's take a plane mirror. The plane mirror actually has, let's say this is an object. Now how is the object visible to you? Go to the basics of it. So how is this mouse visible to me? So the light falls from this window. There's a sunlight that's coming in. Sunlight falls on this, and this reflects the light in all direction. Some of the light falls into my eyes, and I'm able to see that. That's how you see the things. Now look at this rook. I don't know how many of you play chess. So this is rook or hathi. So there is a ray of, so there's light falling on it. Right, light rays get reflected all over the place, right? So now we look at one of the rays here. There's a ray of light that travels here, hits the mirror here. I draw a normal here. I measure the angle of incidence, make another angle of reflection. So after doing all that exercise, what happens is there is a ray of light going this way and it travels back with this in that direction. Now to me, to my eye and to my brain. So eye collects the rays of light and they're transferred to the brain, and brain interprets all this. So brain says light travels in a straight line. So brain has no idea. Basically, I'm not making it up. This is what happens. So brain says light travels in a straight line. To me, the light is coming in this direction. So light was actually produced somewhere here. Mirror doesn't care that light was reflected off the surface. So the brain doesn't care that light was reflected off a mirror. For the brain, the light travels in a straight line. If I'm receiving the light in this direction, then it is actually starting from something here. That's what the brain thinks. And that is how the images are formed. So instead of taking one ray of light, let's take two rays of light. So this is emitting rays of light in all directions. What I have taken now is two rays of light. So there is one ray of light that goes here and that gets reflected here. Brain says, array, it's coming from this direction. And then there is another ray of light that comes this way and gets reflected. Brain says, oh, it's coming from this direction. So wherever those two rays of light meet, that is the image formed. And some students would like me to revise that. I will do that immediately right now. So let's say this was my mirror, and let's say this is a person. Kahan gaya, kahan gaya, kahan gaya? Yahan raha. This is the person. Right, so this is a person. Now let's try to make an image. So there's a ray of light. Let's make a ray of light from his head. The ray of light बना दिया. अब यहाँ पे there is this normal here, and then you got to draw exactly equal angle. क्या बना दिया ये? Let's make it properly. Something is not right. So I'll draw freehand just to save my time here this way. Right. So there's a ray of light that travels here. I'll measure this angle. I'll make exactly equal angle, and you will do much better job than me. So this is a ray of light that travels back, right? Reflected. But the brain, if I'm standing here with my eye there, right? So the eye says, okay, the light travels in this direction. Now let's say there's another ray of light. These colors do not mean the color of light. These are just for illustration, right? So there's a ray of light that travels there. The brain says, okay, so let's make angle of incidence equal to angle of reflection there, right? And then brain says, okay, it's traveling this way. So wherever they meet. So basically, look at this. I'll show that one more time. So there's ray number one that has reflected here, ray number two that has reflected there. Wherever these two rays of light meet, that is the image form. But these rays are never meeting. They're diverging. So what I do is I trace them back. and make them virtually meet. Virtually meeting, not really meeting because there's nothing there. This is the polish, this is a painted surface there. So then this is the image that is formed. Right. Now obviously I'm really sorry because I'm not using these measuring devices. So obviously the image doesn't look very well because the size of the image has to be exactly same, the distance has to be same and all that, but I'm just trying to give you an idea. Now what happens with the image there? So image formed is upright. मतलब उल्टा नहीं बनेगा. Some of the cases you will actually see when we study concave mirrors and convex mirrors, the images can be ulta, है ना, upside down. But the image formed by the plane mirror is upright. सीधे खड़े हो तो सीधा. Image is exactly the same size. Image is as far behind the mirror as you're in front of it. So these are the things you've already studied. I'm not going to revise those. Very quick revision, obviously, right? Now, one thing is your right hand becomes your left hand. So that's lateral inversion that is happening there. So that way the mirror changes at least something. But other than that, your image is exactly you. It's as beautiful as you, obviously, right? Now let's do one of the questions here, just to make practice here with the concepts that you learned in the previous grades, and let's see how much you remember. So for the students, I would advise that you pause the video, try to solve this, and then come back. If you immediately look at what I'm doing, you're not learning anything. A very humble request I make every time when I give you a question, pause the video. Try it. Take 1 minute, 2 minutes, 5 minutes, whatever it takes. No rush. We are learning concept. This is not a speed test. So welcome back. Assuming you have already tried, the angle of incidence is 35. What is the angle of reflection? Angle of incidence kya hai? So this is the original ray of light that is traveling. The very first thing you do is angle of 90 degrees here. And this is 90 degrees line. So basically they're telling me this is 35 degrees. This black angle is 35. So this is also 35. है ना, make sense? Now if that is 35, ये बनाया यहाँ पे, तो अगर ये 35 है तो this is also 35, alternate angles. If that is 35, this is also 35, है ना? Angle of incidence is angle of reflection. See how all these angles are coming out equal to each other. अब इधर आ गया, इधर different है. क्योंकि if you think about this angle was 35 degrees and if you trace this, this is 90 degrees now. If this is 90 degrees, then angle sum property, right? Very basic thing. Sum of angles of a triangle is 180 degrees. तो ये तो 55 आ गया, है ना? वो 35 है तो ये 55 है. ये 55 है तो ये भी 55 है. ये 55 है तो ये भी 55 है क्योंकि all these are alternate angles, है ना? ये और ये भी 55 है. So what is the angle of reflection? Angle of reflection when the ray makes with its last reflection. So the answer is 55 degrees. Very simple, just to get you started here. Now we are going to go more details very soon. So let's move on. So this was about the plane mirror. Let's talk about spherical mirrors. And this is something that you have to study. You already studied in your junior grades, but now you study in more depth. So it's always good to make the foundation solid. So I'm going to revise these concepts in this video and take you further. धीरे धीरे जाएंगे, धीरे धीरे, एकदम से sudden jump नहीं मार सकते. Right, so what is spherical mirror? So there's a sphere, let's say visualize the sphere. Let us say the sphere is made up of glass. Let us say we cut a piece out of it. So there's a glass sphere. I'm cutting this piece out of it as a cross, diamond knife ले लिया, काट दिया उसको, right? Now take this piece. So it's more like, so when you look from side, isn't it like from the side, this thing looks like this. This is your cross section. If you can visualize, it's good. So I've cut it, but you look from the side, it looks like this, right? Now you have two options. Paint it on this side and stand here and watch yourself. Or you could have done this. You could have done the other thing. You paint it on this side and stand here and watch yourself. So either you paint the inside of it or you paint outside of it, right? So these are two different mirrors. They behave exactly differently, completely opposite, and in some cases, but very differently. So if you were to polish it on this side and stand on this side to watch yourself, so this is you, then this kind of mirror is called a concave mirror. Right, and if you polish on the other side, usually what the convention is, object is placed on the left hand side. So even though I could have done this and made you stand there, but the convention says the object should be on the left side. And I'll cover more of these conventions in upcoming videos. But convention is the object should be on the left side of the mirror. So let's place the glass piece like this, and then polish it on this side, and then you stand on this side, and then you try to see your image, and this kind of mirror is called the convex mirror. Right, so concave and convex. So cave, this is a cave here, right? So concave and convex, two different kinds of spherical mirrors. So let's see how they work in principle. So concave mirror, see, I have taken this side and I have polished it on this side. This is all polish. Or convex mirror, you polish or paint on this side, right? So this is convex mirror. Now, when you have this mirror, obviously this was part of a big sphere, right? So this is part of this huge sphere here, right? So now sphere has a center. So that center is called the center of curvature. So again, so this was part of a big sphere. The center of that sphere is called the center of curvature. Now, if you go back to this image, this geometrical center over here, this is called the pole. So, right, so pole is that centerpiece over there. So if you come here, this is the pole. So that's the pole. Now, if you look at the convex mirror, same kind of concept here, nothing new. I mean, nothing different. So this is the center of curvature, and there is a pole over here. Now, the distance between the pole and the center of curvature obviously is the radius of that sphere. So that is called the radius of curvature. So center of curvature, pole, radius of curvature. Now, there's another special point here, which is called the focal point. And coincidentally lies, it's not exactly at the middle of it, but for rough approximation, and I'm going to show you why in the next slide. So one thing, my friends, many of these things are not covered in your regular books that you study in the textbooks. In the textbooks, things are more like differently. I would not call them basics, but they don't cover all these in-depth kind of thing, the reasons behind them. So stay extra focused here. Some things you will not find in your textbooks, but these are good to know, because unless you know this, you're trying to memorize them, ratify them, and you're not understanding why, right? So books will tell you the focal point is between the center of curvature and pole, but Q. No, and when they do derivations, they're more difficult derivations. So I'm going to simplify these things, right? So back to the picture here. So there is a special point here, which is called the focal point. And let's talk about what is focal point. So I'll create another blank slide here and talk about it. So let's say there is a concave mirror here. So I'll go by basics and say, okay, this is my center of curvature. This is my pole, right? Not my pole or center of curvature, the mirrors, pole and center of curvature. Now this line that I have drawn, this line is called the principal axis. Principal axis. Right? It's a line. It extends infinite big, right? It's a long line. Now let's say there is a ray of light that is coming parallel to the principal axis. Let's assume there's a light can fall at any angle, but I'm taking a ray of light that is parallel to the principal axis, right? Now it doesn't look like this. So I'll use freehand. I think freehand I'm doing a better job. So this is my ray of light that is coming parallel to the principal axis. So what would happen after reflection? It will go back. And what I would observe is all these rays of light which are parallel to principal axis, they end up going through a certain point on the principal axis. And that point actually by definition is called the focal point. Means that's where all these are getting focused. Right. So this point where all these are getting focused is called the focal point. And as I said, I'm doing poor job on this whiteboard. I don't know what's going on, but you're going to do much better job than me. And let me do that again, because this is going to confuse many students. So basically, this is what I was trying to say by doing two rays of light. I'll just show you two rays of light. So there's another parallel ray of light here, and this is my ray of light that's going back. So what I observe is the rays of light that are parallel to the principal axis, they end up going through a certain point on the principal axis, and that point is called the focal point. And the distance of the focal point from the principal axis is called the focal length. Not the principal axis, sorry. So distance, so I'll revise everything now. So distance of center of curvature from the pole is called the radius of curvature. Right. Distance of focal point from the pole is called the focal length. And the mirrors are designated, they're specified. Like this is how you tell a mirror a focal length 20 centimeters, 30 centimeters. Now you will actually see that the focal length is actually half of the radius of curvature, or basically this point is midway between those two. Let's try to understand why that is. So let's look at this diagram. So there's a ray of light that comes parallel to the principal axis. So remember, we'll go by the basics. The law of reflection says as soon as the light hits there, you got to draw a normal at this point. Of normal, how do I draw normal? Because see, I know how to draw a normal to a line, but what do you mean by normal to a surface? So let's understand what that means. Now, obviously, everybody knows if there is a line here, I can draw a 90 degrees to that. Right? That's a piece of cake, right? That's a piece of cake. But now let's say I had a circle here. Now what do you mean by normal? What even that means? So I'm saying, okay, there is some point here. Draw 90 degrees to that. What does that even mean? Because there is no line now, right? How do I use my measuring tools? So now at this point, and this is all mathematics, this is not even physics, this is mathematics. So at this point, the direction of the circle is given by the tangent, right? This tangent gives you the direction of that circle. What is 90 degrees to that tangent? 90 degrees to that tangent is the radius at that point. Remember, you studied in your junior grades, tangent and radius are 90 degrees to each other. So if I had to draw 90 degrees line at this point, all I do is join that point with the center. If I have to do 90 degrees line here, this is the 90 degrees line here. This is normal. This is normal at this point. So basically, if you have to draw a normal, sorry, at any point, you join that point to the center of curvature. And let's do the exact same thing here. So I have to make a normal here. Normal kya hai? From this point, I join to the center of curvature. That is my normal. So this line is my normal line. So I'm going to measure the angle with that line. So this angle is theta. That angle is I, right? The angle of incidence, theta. So the ray of light is going to go back at the same angle, theta. Right? That's so obvious, right? If this angle is incidence angle, this angle is theta. So these two angles are equal to each other because one is angle of incidence, this is angle of incidence, and this is angle of reflection. So they are exactly equal. ये हो गया, ठीक है, ये हो गया. अब now look at this angle. So let me paint it green. So this angle, green angle, is equal to green angle. क्यों? क्योंकि that's alternate angle. This line was parallel to this line because we took a ray of light that is parallel to the principal axis. So these rays being parallel, this being the transversal, these two green angles are equal, right? I scribble a lot on the whiteboard, but then I try to clean it up, right? So now this angle is equal to this angle. We know that. But see, what I'm saying is angle 1 is equal to angle 2, alternate angles. But angle 1 is also equal to angle 3 because angle of incidence equal to angle of reflection. So 1 and 2 are alternate, 1 and 3 were equal, so 2 and 3 are equal. So if 2 and 3 are equal, what do I get now? If 2 and 3 are equal, then ACF triangle is an isosceles triangle, and that means CF is equal to AF because that's an isosceles triangle. So CF is equal to AF. Now let's assume that this point A is very close to B. So angle is very small. So the ray of light is parallel to the principal axis but also close to the principal axis. So A is very close to B. So don't you think that AF is same as BF? It's again maths, right? AF is same as BF. So I can write it as BF. And then I can cross the middle part here. So CF is equal to BF. CF is equal to BF ka matlab F is exactly at the center of it. But look at what approximation or what assumption I made. I said if the ray of light is closer to the principal axis and parallel to the principal axis, then this point is there. So basically, all the rays of light that are parallel to the principal axis but closer to the principal axis, they will go through this focal point. Clear? So these rays of light are called the paraxial rays of light. So paraxial rays of light, I'll write it down, paraxial ray of light is something that is parallel and close. This is very important to principal axis. Principal axis. So those two conditions are to be fulfilled in order for the ray of light to go through the focal point. So all the rays of light that are paraxial rays of light will go through the focal point. Rough approximation focal point is between C and the pole. So that part is covered. So now let's talk about non-paraxial rays of light. Non-paraxial rays of light are which are far away from the principal axis. So you can see clearly they are not focused at the principal, because see, the laws of reflection have to be valid. Now this was my 90 degrees line, this angle has to be this angle, but that makes focal point से नहीं जाएगी वो ray of light, right? Only for the rays of light which are closer. यहाँ भी देखो, this angle is equal to this angle, but that makes this line is not going through the focal point. So when will this be useful? कि भाई rays of light that are parallel to principal axis go through the focal point. That's only valid when the rays of light are closer, मतलब small aperture. So what that means by small aperture is this. So let me actually make another slide and show you what I mean. So let's say there was a sphere here, and you cut a tiny piece out of it. Maybe यहाँ से यहाँ तक ये cut कर लिया, है ना? So maybe यहाँ से यहाँ तक ऐसे cut कर लिया. These are small aperture mirrors, and for these it is valid. पर ऐसा नहीं कि इतना बड़ा pick कर लिया, then it is not going to work. Right? But why would you have those mirrors? You need those mirrors. So look at the scenarios like these oil filled pipes. These actually, this is an application of concave mirror. So remember, all the rays of light that are parallel to the principal axis, they focus on the focal point. But I can use that because see, think about this way, the rays of light coming parallel matlab kya? If I have a concave surface here, and the rays of light are coming from the sun is far away, so all those rays of light are coming parallel, those parallel rays will focus at one point. So at that point I get so much of energy, I get focused energy, I can use that heat. And this is what this solar heating appliance is using. It is oil filled pipe, all those rays of light are supposed to be focused at the focal point. But unfortunately, we need big things here, but big things, it is not going to work. So what you do is you use parabolic. You do not use spherical, you use a parabolic. So in your math classes, you have already studied parabolas. So when you need big mirrors, you don't use spheres, you use parabolas. So your dish antenna, it's basically a mirror. You don't see your faces in that, but it's a mirror because it's reflecting the radio waves and the microwaves. It's actually a mirror. All these rays of light coming parallel to the principal axis, they are focused at this focal point, and this is the receiver that is getting it. But this is a huge mirror. The rays of light are not going to be paraxial, and that is why the dish antenna is parabolic in shape, right? Now the question is, some of my students immediately ask, if parabola works for big and small, why don't we always use parabola? Why do we even use sphere? Because it is costlier to make parabolas, right? To fabricate this takes more resources, more sophistication. So to make parabolic mirrors is more expensive. So if you need smaller mirrors, like to see your face, or a dentist mirror, you're going to use spherical mirrors. For large mirrors, you're going to use parabolic mirrors. So with that, let's move on. So now remember, like laws are laws, right? So plane mirrors, spherical mirrors, what kind of mirrors doesn't really matter. Laws are laws. So rays of light coming and striking a surface are going to be reflected back in such a way that the angle of incidence is equal to angle of reflection. So let's understand what that means actually. So let's say I have a spherical mirror here. Okay, there's a spherical mirror, and then there is this principal axis, right? This is your focal point, and this is your center of curvature. Now any ray of light that comes here, it's easy because you can take this point and join with the center of curvature. This is the angle of incidence. Then you can draw. Remember, this ray is not parallel to principal axis. So now you can draw this normal and measure that angle, and then measure another angle on the other side, and this is equal to I, and the ray of light is reflected back. You can do that. So you can use your protectors and measure these angles. But there are three special rays. If you use those rays, you don't need protector, and that's why we are working on that. So let me first explain them, and then I'll go to that picture. So let's say there is a ray of light that comes parallel to the principal axis. Now I know I don't need a compass here, a protector, sorry. I don't need a protector, because why would I do that? Even if I take a protector and measure this, I'm going to get the ray of light going through the focal point. So ho gaya. If there's a ray of light that's going parallel to the principal axis, it goes back through the focal point. ठीक है, simple हो गया. ये special ray है. If the ray of light is parallel, it goes through the focal point. Second special ray is ulta of this. So if there's a ray of light that goes through the focal point like this. Now if you do the same kind of thingy, you will see that the ray of light will come back parallel to the principal axis. So what is the second special ray? Second special ray is the ray of light that goes through the focal point is going to come out parallel to the principal axis. It's completely opposite of that, and there it goes by the principle of reversibility of light. If there's a ray of light parallel, it goes through the focal point. If there's a ray through the focal point, it goes back through parallel. That's it. There's another special ray. That special ray, okay, let me explain that before that. So let's say this is my plane mirror. Okay. Now let's say there is a ray of light that falls 90 degrees to that. It's 90 degrees ray. So what is the angle of incidence? Angle of incidence is 0, because you measure the angle of incidence with the normal line. This ray of light itself is the normal line. So if angle of incidence is 0, angle of reflection is 0. So the light will go back. It will not deviate, it will just go back, right? Same thing. Let's say there is a ray of light that goes through the center of curvature. So this line is going through the center of, choti ho gayi. So let me draw that one more time. This whiteboard is a little tricky to use. Yeah. So now let's say there's a ray of light that is going through the center of curvature. The very first thing you do is, at this point you draw the normal, which is the line from this point to the center of curvature, but this is the incident ray. So the angle of incidence is 0. Angle of reflection has to be 0. So go by that logic. Don't rectify, don't memorize this. So ray of light coming through the center of curvature actually have incidence angle 0. So it has to have reflection angle 0. It will go back through the same path. So these are the special rays of light. Look at the first ray of light. It is going parallel to the principal axis. It will go back through the focal point. No measuring device needed. Now the second ray of light here is going through the focal point. After reflection, it goes back parallel to the principal axis. No measuring device needed. The third ray of light here, right? The third ray of light is going through the center of curvature. So it will go back parallel to it is going through the center of curvature. So incidence angle 0, reflection angle 0. So it goes through this path and then comes back along the same path. So these are the three special rays of light. And how do we use them? Let me show you how you can use them. Now, remember how we made the images in plane surfaces? We find two rays of light wherever they meet, that is the image and all that. So I'm just going to give you a brief introduction about how the image is formed here in the upcoming video, because this video is too big now. So I'm going to publish it in next week's video. I'm going to show you how the images are formed. But let's get started here. So let's say this is a concave mirror. So the very first thing I do on this is I draw the principal axis here, and I show the center of curvature, the pole, and the focal point, right? So these are the 3 points there. Now let us say I put an object here. I can put object anywhere, and as you will see in upcoming video, like in the case of plane mirror, the image is same size, upright, and same distance. नहीं, ऐसा नहीं होता. Image here can be big, small, real or virtual, depending on where you keep it. Right? So let's say this is my object. Now what would happen is the rays of light from the light bulb here maybe or the sun here will fall on this, and this is going to reflect light in all directions, right? All possible directions. So obviously there are so many rays of light that are going and striking this mirror, infinite many. But I'm going to take any of the two special ones that I studied just now. So again, I'm going to tell you one more time. So what I'm doing now is there are rays of light that are going and striking the mirror in all possible directions. I will take any two rays of light, but I will prefer the special rays of light because then I don't need any measuring device. So, okay, I'll use my freehand tool here. So the ray of light goes this way. Let's call it ray number one. So ray number one strikes the mirror. I don't need any measurements there of angles, obviously no measurements because this ray was parallel. It come out through the focal point. So this is my ray number one, right? That is going parallel, comes out through the focal point. Now let's take another ray of light here, and this ray of light I'll color green, and this ray of light is going this way, but then it has to come out parallel to the principal axis, right? So I'll do again a little better maybe. Yeah. So this is my ray number two that is going through the focal point. It comes out parallel to the principal axis. So wherever these two rays of light meet, that is the image form. So let's call this point A. The image of A is formed here. Let's call it A dash. And this was B. B will be on the principal axis. So this arrow, I'll shorten that. So basically, this is what I'm trying to say. This is your image. The arrow there was the object, and this A dash, this arrow is the image. So now look at the kind of image you have. First of all, the image is inverted. Right, the image is inverted, it is smaller also. And then it's real. Look at, it's the real image. You can take it on a screen. If you put a screen at this point, it is going to form the image on the screen. You don't have to put a screen. You can put your palm there. Your image of that arrow is going to be formed on your palm. The rays of light are really meeting. Remember in the case of plane mirror, I traced them back and virtually made them meet. Here they are really meeting. Look at this. So this is a real image. Now in upcoming videos, and I have to end this because it's getting too big. So we will talk about the image formation in concave and convex mirrors, and we'll do in-depth study on that. Right, so let's wind it up with a revision of whatever we did here. So in a summary, in a nutshell, so a ray that is parallel to the principal axis passes through the focal point. Ray of light through the focal point goes back parallel to the principal axis. Any ray of light going through the center of curvature is going to retrace its own path. Now, we tried that. This slide was supposed to show you how the image is formed. A very humble request one more time is subscribe to this channel so that when upcoming videos come in, you can see the notifications. Also share this with your friends, because if more students are watching, I think it is getting fruitful, and then I publish more videos. Because if only few people are watching this, then sometimes it's like, okay, right, you understand my point, right? So try to basically share this with your friends so that I can create more videos. So let's wind up with a nice quote here. Your dreams are calling you. Now it's completely up to you whether you accept it or decline it. I'm going to publish more videos every few days now so that we can complete this ray optics, and I'll see you soon. I think maybe 4 or 5 days from now. So thank you. Bye bye.